Before the first star, before the first atom, there was nothing. Or was there? Try to imagine it, not just darkness, but an absence of the very concept of dark and light. Not silence, but a void where sound could not exist. A canvas without dimensions. A clock without time. This is the ultimate quiet. The hush before the universe drew its first breath. For millennia, we've told stories to fill this emptiness, to give shape to the shapeless. We imagined a cosmic egg, Iron Chagarbah, shimmering in the void, holding all potential within its shell. We dreamt of a great serpent biting its own tail, a cycle of eternal return. We spoke of a chaotic abyss, a swirling, formless sea from which order would one day arise. These weren't just tales. They were our first attempts to answer the greatest question. Where did everything come from? For so long, creation was the domain of gods and myths. It was an act of divine will, a story told in sacred texts. But then, a new kind of story began to unfold, not on ancient scrolls, but in the meticulous language of mathematics and observation. In the early 20th century, a Belgian priest and astronomer named Georges Lemaître dared to imagine a different beginning. He didn't see a divine hand, but a primeval atom, a single, infinitely dense point containing all the matter and energy of the universe. He proposed a day without a yesterday, an audacious, almost poetic idea, born from the cold, hard lines of Einstein's equations. At first, it sounded like science fiction, a new myth for a new age. The scientific community was skeptical. The idea of a beginning, a moment of creation, felt too much like the old stories they were trying to move beyond. The universe, they believed, was eternal, unchanging, a steady state. But the cosmos had other plans. Far away, at the Mount Wilson Observatory, an astronomer named Edwin Hubble was methodically charting the heavens. He wasn't looking for a beginning. He was simply measuring the distance to faraway nebulae. But his telescope revealed something astonishing, something that would change everything. He noticed that the light from distant galaxies was stretched, shifted toward the red end of the spectrum. This redshift was a cosmic Doppler effect. It meant that these galaxies weren't just sitting there. They were rushing away from us, and from each other. The farther away a galaxy was, the faster it seemed to flee. The conclusion was inescapable, and it was profound. The universe was not static. It was expanding. If the universe is expanding today, then yesterday it must have been smaller, and the day before that, smaller still. The implications of Hubble's discovery were staggering. If you could run the cosmic film in reverse, everything every star, every galaxy, every planet would rush back together. The vast, cold emptiness of space would shrink, compressing into a smaller, hotter, denser state. The great expanse would collapse inward, hurtling back toward a single, unimaginable point of origin. Lemaître's primeval atom was no longer a myth. It was a destination at the very beginning of time. So, let's return to that initial void, that absolute stillness. Can you feel it now? Not as an empty stage, but as a point of infinite potential. A tension building in the fabric of nothingness. All the laws of physics, all the wonders of life, all the light of a trillion stars, coiled into a space smaller than a grain of sand. The cosmic egg of the ancients reimagined. There is no sound, no light, no time. Just a silent gathering pressure, a single, perfect symmetry, holding everything in a fragile balance. The universe is waiting. A tremor is about to pass through the void. The grandest story is on the verge of beginning, not with a word, but with an explosion that will give birth to space itself. The hush is about to break. The clock is about to start ticking. The first moment is almost here. An entire cosmos, held in a breath, waiting to be exhaled. Step into the silence, into the moment just after the very first moment. There are no clocks here, because time itself is just being born. We are in an era so brief, it makes a blink of an eye feel like an eternity. This is the Planck, a point in cosmic history where our laws of physics, the familiar rules of gravity and motion, simply dissolve. Imagine a canvas, smaller than the smallest thing you can possibly think of. A single point of unimaginable energy. Here, space and time are not the smooth fabric we know. Instead, they are a roiling, chaotic froth. Physicists call it quantum foam. It's a place where tiny, fleeting universes could be bubbling in and out of existence. A storm of possibilities where direction up, down, left, right has no meaning. Past and future are scrambled together in a single, intense instant. This isn't just an empty void. It's a cauldron of pure potential. A place where the rules of reality haven't yet been written. It's less like a place and more like a thought. A fleeting dream before the universe truly awakens. And then, something extraordinary happens. An event that will define the entire future of the cosmos. From this teeny frenzied point, an expansion begins. But this is no ordinary explosion. It's a hyper-acceleration so vast and so fast it defies all comparison. It's a moment called inflation. Think of a single, deep breath, filling an intricate paper lantern in an infinite darkness. In a fraction of a second, the lantern doesn't just get bigger. It expands from a folded speck to a sphere larger than a galaxy, its delicate pattern stretching smooth and vast. This isn't a blast pushing things outward through space. This is space itself, the very fabric of reality, stretching at an inconceivable rate. It's as if a single ripple on a perfectly still pond was suddenly pulled taut, stretching across a boundless ocean in an instant. This incredible stretching smoothed out the infant universe, ironing out the chaotic wrinkles of the quantum foam, making it incredibly uniform and flat on the largest scales. It's the reason why the universe looks so similar in all directions today. A cosmic mystery solved by this single, violent exhalation. What drove this unimaginable expansion? Scientists imagine a force, a field of energy that permeated everything in that first instant. They call it the inflattened field. You can think of it not as a thing, but as a presence, a cosmic pressure that couldn't be contained. It's like the hum before a great sound, the tension in the air before a storm breaks. This field was filled with energy, and as it settled down to a lower energy state, it released its power into the expansion of space itself. It was the engine of creation, a mechanism that took the chaotic point of the Big Bang and stretched it into the vast arena we now inhabit. It was a fleeting but all-powerful force, lasting for only a sliver of a second before vanishing. Its job done. Its legacy is the sheer scale of our cosmos, the foundation upon which everything else would be built. The universe we see is the echo of that field's brief, glorious reign. And within this storm, something subtle and beautiful was happening. The quantum foam, the chaotic fizz of energy at the very beginning, wasn't perfectly smooth. It had tiny, random fluctuations, microscopic jitters in the density of energy. As inflation stretched the universe, it stretched these tiny fluctuations as well. They went from being infinitesimally small to astronomically large. It's like taking a tiny, invisible imperfection in a piece of glass and stretching it until it becomes a visible wave running through the entire pane. These weren't just random patterns. They were the seeds of everything. These slight variations in density, stretched across the cosmos, were the primordial blueprints for structure. They were the faint whispers of future galaxies, the gravitational starting points where matter would one day gather. The grand tapestry of stars and nebulae we see in the night sky began as quantum noise, stretched to cosmic proportions by the incredible breath of inflation. It feels less like physics and more like a creation myth, a silent drumbeat that stretches the skin of the world, making it vast and ready. Winds, sent by hidden gods, shaping the void into a home for stars. In this ancient moment, the universe wasn't just expanding, it was being inscribed with its own destiny. The faint patterns being stretched across the fabric of space-time were like invisible ink, a message that would only become clear billions of years later as gravity began its slow, patient work. As the inflationary era ended, space was now vast, smooth, and filled with a hot, uniform soup of fundamental particles. The frantic energy of the inflaton field had been converted into the matter and radiation that would form our universe. The stage was set. The initial chaos had been tamed and stretched into an enormous, quiet canvas. Across its surface, the faintest of patterns were forming, the first lines in the epic story of the cosmos, as space itself continued its relentless race outward into the unknown. As the echoes of the Big Bang fade, the universe, still impossibly young, embarks on a new phase of its existence. The searing, unified brilliance begins to cool. And from this cooling, a tempest of particles is born. Imagine a forge white-hot and blinding, where the fundamental forces of nature are separating, like metals of different temperaments solidifying from a molten blend. In this primordial furnace, the universe is no longer a single, perfect point of light, but a chaotic, roiling sea of energy giving birth to matter. For every particle of matter that springs into existence, a mirror image, an antiparticle, is also created. Matter and antimatter, perfect opposites, destined to annihilate each other on contact, returning to pure energy. It's a cosmic dance of creation and destruction, a relentless cycle playing out trillions upon trillions of times every microsecond. If this dance were perfectly balanced, every particle meeting its antiparticle, the universe would have eventually cooled into a vast, empty void of faint light, with nothing left to form stars, planets, or us. But the universe, it seems, had a subtle preference, a tiny, almost imperceptible imbalance, a sleight of hand in the laws of physics. For every billion pairs of matter and antimatter that annihilated each other, a single, solitary particle of matter was left behind, a cosmic rounding error, a whisper of asymmetry that saved everything from nothingness. It was as if the cosmic smiths, hammering out reality on the anvil of space-time, intentionally forged one extra key, a key that would unlock a future filled with substance. This great imbalance is the original sin of our universe, the beautiful flaw that allowed for our existence. In these first moments, the universe is a quark-gluon plasma, a state of matter so hot and dense that the fundamental building blocks of protons and neutrons, quarks and their binding force carriers, gluons, cannot yet combine. They swirl freely in a seething, primordial, super turbulent ocean of potential. There are no atoms, no structures, just this fundamental chaos. It is a time of perfect symmetry in a way. Everything is everywhere, indistinguishable, a featureless temp. But this perfection cannot last. The universe continues to cool, to expand, and as it does, it begins to break. This isn't a violent shattering, but a beautiful, poetic breaking of symmetries. Think of steam cooling into water, then freezing into the intricate, unique patterns of a snowflake. The formless gains form. The perfect sameness gives way to a world with features, with rules, with individuality. As the temperature drops, the forces that govern the universe begin to take on their distinct characters. Gravity had already split off, and now the strong and electroweak forces part ways. And in this cooling chaos, some particles simply stop interacting. Neutrinos, the ghosts of the particle world, decouple from the rest of the cosmic soup. They stream away, becoming silent messengers from this ancient epoch, traveling unimpeded through space and time, carrying secrets of the universe's first minute. Their departure is like a soft chime, marking the passage of time in a cosmos that has not yet known stars or clocks. The cooling continues. The quark-gluon plasma thins, the frantic energy subsides, and a profound change is about to occur. The wild, free-roaming quarks begin to feel the irresistible pull of the strong nuclear force. The chaos is beginning to organize itself. The temperature drops below a critical threshold, and suddenly, the universe is no longer a sea of free quarks. They are captured, bound together in trios, by the powerful glue of the gluons. For the first time, the universe forges protons and neutrons, the first stable, composite scaffolds of matter. The very first pillars of the cosmos we know are being erected, patiently waiting in the fading heat of creation. In the lingering echo of that first colossal sound, the universe was still a searing, incandescent sea. Imagine a light so pure, so potent, that nothing could yet take solid form. For a fleeting moment, the cosmos was a furnace hotter than the heart of any star that would ever be born. This was the crucible where the very first atoms would be forged. But this creation wasn't a sudden, explosive event. It was a delicate, cosmic dance, dictated by temperature and time. As the universe expanded, it began to cool. This cooling was the key. Protons and neutrons, the building blocks of atomic nuclei, were frantically colliding, desperate to bind together. But in the intense heat, any fragile bond they formed was instantly shattered by energy. Photons, particles of light, acting like microscopic hammers. This was the deuterium bottleneck. Deuterium, a simple nucleus of one proton and one neutron, is the first essential step towards building heavier elements. But it's also incredibly fragile. For what felt like an eternity, but it was merely a couple of minutes, the universe was too hot for deuterium to survive. It was like trying to build a sandcastle in a hurricane. No sooner was a pair of particles joined than they were blasted apart. The cosmic forge was too wild, too hot. Then, the universe cooled to a critical threshold just below 1 billion degrees. The photon storm subsided. The hammers of light lost their shattering force. Suddenly, deuterium could hold together. The bottleneck was broken, and a furious, brief fire of creation ignited across the cosmos. Deuterium nuclei, now stable, rapidly captured more protons and neutrons. 2 deuterium nuclei could fuse to form a nucleus of helium-3, or a robust, incredibly stable nucleus of helium-4, with 2 protons and 2 neutrons. This process was breathtakingly efficient. In a mere 3 minutes, almost all the free neutrons in the universe were locked away inside helium-4 nuclei. Think of it like a divine kill, a story told in ancient myths where gods shaped the world from fire and clay. Here, the gods were the fundamental forces of nature, and the clay was the primordial plasma. The hearth of the cosmos was lit, and in its fleeting glow, the first elements were baked into existence. The universe had cooked up its first stable matter. When the fire of this cosmic kill finally dimmed, after about 20 minutes, the composition of the universe was set for a very long time. For every 10 protons that remained, there was 1 nucleus of helium-4. This left a vast ocean of hydrogen, but also trace amounts of the ingredients that didn't quite make it into the final helium product. Little leftover deuterium, a sprinkle of helium-3, and an even tinier, almost imperceptible whisper of lithium-7. These were the ashes of that first fire, a chemical signature imprinted on the cosmos itself. Centuries later, long after these events unfolded, curious minds, like Ralph Alt, Hans Botti, and George Gamow would learn to read these ashes. They looked at the abundance of elements in the universe today and reverse engineered the recipe of creation. They became cosmic archaeologists, deciphering the story of this first furnace by studying its faint, ancient embers scattered across the stars. Their work allowed us to gaze back in time and witness the universe in its first moments of chemical identity. As the universe continued its relentless expansion, the heat from this great forging dissipated, the embers of creation dimmed, the density of matter thinned, and the cosmic furnace grew quiet. The light that had once filled all of space, trapping matter in a brilliant fog, was now stretched and cooled. The universe was on the cusp of becoming transparent, a vast, dark stage waiting for the next act. The elements were forged, the particles had found their place, and a quiet expectancy settled over the cosmos. A new era was about to begin. Imagine, for 380,000 years, the entire universe was an impenetrable fog, a blazing, dense soup of protons, neutrons, and electrons, so hot and chaotic that light itself was trapped, bouncing endlessly from one particle to another like a pinball in an infinite machine. No stars, no galaxies, just a brilliant, opaque plasma. But the universe, as always, was expanding and cooling, and as it cooled, it approached a critical threshold, a moment of profound transformation. The temperature dropped to about 3,000 Kelvin. Suddenly, the frantic energy of the cosmos subsided just enough. The free-roaming electrons, which had been zipping around like a swarm of agitated bees, finally lost enough energy to be captured by the waiting atomic nuclei. One by one, they settled into stable orbits, forming the first neutral atoms, mostly hydrogen and helium. This wasn't a violent event. It was a quiet, cosmic settling. Picture a snow globe that's been shaken violently for ages. And then, all at once, the shaking stops. The snowflakes begin to gently drift down, creating clarity where there was once a blizzard. The universe was that snow globe. The fog cleared. For the very first time, the cosmos became transparent, and in that instant of clearing, all the light that had been trapped inside the plasma was set free. A colossal, universe-wide flash of light was unleashed, traveling unimpeded in all directions. This is the oldest light we can ever see. It's the first light, and it's still traveling today. For 13.8 billion years, it has been journeying across the expanding fabric of as the universe stretched, this light is stretched with it, its wavelength getting longer, and longer its energy dropping, shifting from a brilliant white-hot glow into the invisible, faint chill of microwaves. This ancient light is what we now call the cosmic microwave background, or the CMB. It's not coming from any particular star or galaxy. It's coming from everywhere at once. It's the afterglow of creation itself, a whisper from the dawn of time. The story of its discovery is one of science's most beautiful accidents. In 1964, two radio astronomers, Arno Penzias and Robert Wilson, were working with a massive horn-shaped antenna in New Jersey. They were trying to do some sensitive radio astronomy, but they were plagued by a persistent, faint, and uniform hiss coming from every direction they pointed their antenna. It was a noise they couldn't explain and couldn't get rid of. They thought it might be interference from New York City. It wasn't. They wondered if it was their equipment. They checked every wire and connection. Then, they noticed a pair of pigeons had been roosting inside the antenna, leaving behind what they delicately called a white, dielectric material. They cleaned out the pigeons and their mess, hoping that would solve it. The hiss remained. Frustrated, they happened to talk with a group of physicists at nearby Princeton University who had a theory. These physicists, led by Robert Dick, had predicted that if the Big Bang had happened, there should be a faint, residual glow left over from the hot, early universe, now cooled to just a few degrees above absolute zero. When Penzias and Wilson described their persistent, unavoidable noise, the Princeton group knew immediately what it was. Penzias and Wilson hadn't found pigeon droppings. They had stumbled upon the echo of the Big Bang. They had heard the oldest sound in the universe. That discovery opened a new window into our cosmic origins. Later, satellites like COBE, WMAP, and then the Planck satellite took our understanding to a whole new level. They mapped this ancient light with breathtaking precision, revealing that the hiss wasn't perfectly uniform. It had tiny, almost imperceptible temperature fluctuations, hot and cold spots that varied by only 1 part in 100,000. These are the faint freckles on the face of the infant universe. They look like a star map, tattooed in baby blue static, a relic lullaby from the cosmos's nursery. Those minuscule variations were the seeds of all future structure. The slightly denser, cooler spots were where gravity would begin its patient work, pulling matter together over billions of years to form the first stars, the first galaxies, and eventually US. So as we peer out into the night sky, we are looking back in time, and with our radio telescopes, we can look back to this very moment. We can see the light from that instant when the universe first became clear, a brilliant flash, released to stream freely through newborn space, while the first atoms of matter began to drift silently into the deepening dark, gathering in the places that would one day light up the sky. Imagine the universe, now 380,000 years old. The blinding plasma has cooled, and light, for the first time, streams freely across space. This is the cosmic microwave background, the afterglow of creation we can still see today. But as this light journeyed onward, the universe itself slipped into a profound and quiet darkness. This was the cosmic dark age, a period that would last for hundreds of millions of years. The cosmos was now a vast, transparent, and silent expanse, filled with a thin mist of neutral hydrogen and helium atoms. No stars, no galaxies, just the patient, invisible hand of gravity at work. Throughout this immense darkness, something unseen was gathering. Dark matter, the mysterious scaffold of the universe, was slowly pulling the ordinary matter into its gravitational embrace. In countless locations, these invisible halos of dark matter became the cosmic cradles, collecting gas into ever denser clouds. For millions upon millions of years, the process was achingly slow. Gravity was the only force shaping the future. Think of it as a quiet, cosmic ocean, with currents of dark matter gently swirling, pulling together the first ingredients for stars. Inside these growing clumps of hydrogen, the pressure and temperature began to climb. It was a subtle drama, unfolding in complete darkness. A slow-motion collapse, a gathering of potential, a promise of light yet to be born. Then, after an epoch of silence, a new dawn began to break. Deep within the densest cores of these primordial gas clouds, the pressure and temperature reached a critical point. A flicker, then a roar. Nuclear fusion ignited. The first stars were born. These were not like the stars we see today. They were giants, monsters of the cosmos, known as Population 3 stars. Hundreds, perhaps even thousands of times more massive than our own sun. They burned with an almost unimaginable intensity. Their light was fierce, blazing with brilliant blue and ultraviolet radiation. They were the first fires stolen from the eternal night, the first torchbearers in a sleeping sky. Their existence was breathtakingly brief. While a star like our sun will live for 10 billion years, these giants burned through their fuel in just a few million. They lived fast and died young, but their impact was monumental. As their powerful light flooded the surrounding hydrogen gas, it stripped electrons from their atoms, a process called reionization. It was as if someone had thrown a switch, turning the lights back on across the universe, one bubble of brightness at a time. Each star was a beacon, its brilliant, short-lived incandescence pushing back the shadows. These primordial suns were not just points of light, they were engines of creation. In their fiery hearts and explosive deaths, they forged the first heavy elements: carbon, oxygen, iron, the very building blocks of future stars, planets, and ultimately, life itself. Picture it, a vast, dark sea, and then, one by one, pinpricks of light begin to appear, each one a fleeting, brilliant island in the cosmic ocean. Their light begins to creep across the void, illuminating the hydrogen fog, waking the universe from its long slumber. The first dawn was not a single sunrise, but a slow, spreading tide of light, a gentle, expanding vista of illumination, pushing back the longest night the universe has ever known. The silence was broken, not with a bang, but with the quiet, persistent glow of the first stars, setting the stage for everything that was to come. And across the cosmic sea, the light just keeps spreading. From the uniform haze of the early universe, a grand design begins to emerge over hundreds of millions of years. Gravity, the patient, silent choreographer, starts its slow, inexorable work. The cosmic fog, once so evenly spread, begins to thin in some regions and thicken in others. Tiny, almost imperceptible fluctuations in density, mere whispers in the cosmic dawn, become the seeds of everything that will follow. Where matter is slightly denser, gravity's pull is slightly stronger. More matter is drawn in, making the pull stronger still. It's a process of gravitational amplification, a feedback loop that plays out over eons. The first structures to form are not galaxies, but vast, gossamer sheets and long, winding filaments of dark matter and gas. This is the cosmic web, the underlying skeleton of the universe. Picture it as a celestial network of immense proportions, great filaments, like the roots of a cosmic tree or the shimmering threads of a spider's web, stretch for millions of light years across space. They are the highways of the cosmos, funneling gas and dark matter toward their intersections. Between these glowing threads lie the great cosmic voids, immense, underdense bubbles of near-nothing, like quiet, dark oceans separating continents of light. At the nodes of this web, where the filaments cross and matter concentrates, the first galaxies are born. These proto-galaxies are small, chaotic, and blazing with the light of their firstborn stars. Gravity continues its dance, pulling these infant galaxies together. They collide, they merge, they dance in gravitational embraces that can last for billions of years. Through these mergers, galaxies grow, their structures evolving. Some settle into elegant, spinning spirals, their arms tracing pathways of new star formation, glittering with the blue light of young, massive stars. Others, the products of more violent, multiple mergers, exhaust their gas and settle into the serene, golden glow of elliptical galaxies, ancient cities of old stars. Within these swirling stellar cities, a new drama unfolds. The life cycles of stars enrich the cosmos. Massive stars live fast and die young, exploding as supernova. These cataclysmic events are not just endings, they are acts of creation, seeding the surrounding gas clouds with heavier elements forged in their stellar hearts. This enriched material becomes the building blocks for new generations of stars, and eventually, for planets and for life itself. The universe is recycling, constantly remaking itself from the ashes of its past, and at the very heart of these nascent galaxies, another mystery is taking root. In the dense central cores, the seeds of supermassive black holes are sown, whether from the collapse of a single, gargantuan first-generation star or from the runaway merger of smaller black holes. These objects of immense gravity begin to grow. As gas and stars spiral inward, they form a brilliant accretion disk, a swirling vortex of matter heated to millions of degrees, releasing a torrent of light that can outshine the entire galaxy. This is the quiet, deadly light from the edge of oblivion, a beacon signaling the presence of a sleeping giant at the galaxy's core. For millennia, we have looked at the sky and seen patterns, weaving our own myths to make sense of the vastness. We imagined a world tree, its branches holding the heavens, its roots digging into the unknown. We conceived of Indra's net, a cosmic web where every jewel at every intersection reflects all the others. A metaphor for the interconnectedness of all things. We spoke of the fates, weaving the threads of destiny on a celestial loom. It seems our intuition, our need for story, was touching upon a fundamental truth of the cosmos. When our own astronomers first began to systematically map the heavens, charting the positions of distant galaxies, they were, in a way, retracing these mythic threads. Early surveys, painstakingly compiled, began to reveal that galaxies weren't scattered randomly. They were arranged in long chains and great walls, bordering vast, empty regions. We were uncovering the filaments and voids of the cosmic web, our telescopes providing the first concrete evidence of this grand, underlying architecture. We were, for the first time, seeing the weave. And the loom has not stopped. The weaving continues. Gravity still pulls. Galaxies still drift and merge. Stars are still being born from cosmic dust, and new threads are still being spun across the voids. The architecture of space is not a finished monument to be observed, but a living, breathing tapestry that is still unfolding. Its full expanse, stretching far beyond our current sight, with miles and miles of thread yet to be woven. Have you ever stood in a vast, silent field at night and felt that you weren't entirely alone? It's not a feeling of being watched, but a sense of presence, something unseen but profoundly there. Our universe shares this feeling. For all the glittering stars and swirling galaxies we can see, we are surrounded by invisible partners, cosmic ghosts that shape everything. This isn't science fiction. It's the strange and beautiful reality of our cosmos. It all started with a puzzle. In the 1970s, an astronomer named Vera Rubin was watching spiral galaxies spin. She expected the stars on the outer edges to move slower, like planets far from our sun, but they didn't. They were moving just as fast as the stars near the center. It was as if something unseen, some enormous halo of invisible mass, was gripping the entire galaxy, providing extra gravity to keep those stars from flying off into the void. This was the first major clue for what we now call dark matter. We've never touched it, never seen Italiano. It doesn't shine, it doesn't reflect light, it doesn't even cast a shadow. So how can we be so sure it's there? Imagine walking through a forest on a windy day. You can't see the wind itself, but you see its effects everywhere: the swaying branches, the rustling leaves, the force pushing against you. Dark matter is like that cosmic wind. We see its influence in how galaxies clump together to form massive clusters. We see it bend the light from distant objects, a phenomenon called gravitational lensing, where its immense gravity acts like a cosmic magnifying glass, distorting and amplifying the light from whatever lies behind it. The most striking evidence is the bullet cluster to colliding galaxy clusters, where we can literally see the normal, glowing matter gets separated from the invisible mass that sails right through. Its gravitational effects still clearly mapped. Whatever it is, there's about 5 times more of it than all the stuff that makes up you. Me, the planets, and every star we've ever seen. But the story gets stranger. While dark matter pulls things together, another, even more mysterious entity is pushing everything apart. For most of the 20th century, we thought the universe's expansion, which began with the Big Bang, was slowing down. Gravity, after all, should be pulling everything back together. But in the late 1990s, two teams of astronomers were using a special kind of exploding star, a Type Ia supernova. As cosmic mile markers, these supernovas have a consistent brightness, so we can tell how far away they are. And when they looked at the most distant ones, they found something shocking. Those distant galaxies weren't slowing down, they were speeding up. The universe's expansion is accelerating. Something is acting like a gentle, persistent pressure in the void, pushing space itself to expand faster and faster. We call this dark energy. It's not like any energy we know. It seems to be a property of space itself. The more space there is, the more of this energy there is, pushing it to expand even more. It's like an invisible wind filling the sails of the cosmos, stretching the fabric of reality. It's subtle, a quiet pressure in the vast emptiness between galaxies, but over cosmic scales, it's the most powerful force in the universe, making up nearly 70% of everything that exists. So, here we are, living in a universe where about 95% of its content is a complete mystery. The things that shine the stars, the nebulas, the breathtaking galactic spirals are just the foam on a vast, dark ocean. Does this diminish the wonder? I think it deepens it. It's a profound lesson in humility. It reminds us that what we see is not all there is, that the most fundamental truths are often hidden just beyond our perception. It adds a layer of uncanny beauty to the night sky, knowing that the real drama, the great cosmic tug-of-war between dark matter's pull and dark energy's push, is happening silently, invisibly, all around us. This cosmic battle will determine our ultimate fate. Will the accelerating expansion continue forever, stretching galaxies so far apart that the sky eventually goes dark, leading to a cold, quiet, heat death? Will dark energy one day reverse, causing a big crunch? Or will it grow so strong that it rips apart galaxies, stars, planets, and even atoms themselves in a big rip? We don't know. We stand on the shore of this dark ocean, peering into its depths, knowing only that the universe is far stranger and more magnificent than we ever dared to imagine as we gaze into the darkness between the stars. Are we looking at emptiness? Or are we looking at the very thing that holds the key to everything? And so, the universe breathes out and then breathes in after the long, quiet expansion. Gravity begins to pull things back together, not into another single point, but into countless swirling pockets of possibility. Imagine a vast, dark cloud, kilometers wide, adrift in the interstellar sea. It's not empty. It's a ghost of stars that lived and died long ago, a cold, thin mist of hydrogen, helium, and the dust of 1,000 supernovas. This is our inheritance. The recycled stardust from which we will be made, slowly, almost imperceptibly. Something shifts, a whisper of gravity, perhaps nudged by the shockwave of a distant exploding star, causes a slight overdensity. Clump. A clump, and where there is a clump, gravity has a toehold. The cloud begins to collapse, falling in on itself, spinning faster and faster like a celestial figure skater pulling in their arms. At the center, the pressure and heat build, a furious furnace igniting in the dark. A star is being born. Our star, the sun. But not all the material falls into this stellar heart. Around the young, blazing sun, a vast, flat, rotating disk of gas and dust spreads out a protoplanetary disk. This is the leftover batter, the cosmic potter's wheel from which the planets will be sculpted. Within this spinning expanse, the magic of accretion begins. It's not a violent process, not at first. Think of it as a slow, patient rain. Tiny dust grains, glittering with ice and sticky with organic compounds, gently bump into each other. Static electricity makes them cling, then more join, and more a dust bunny becomes a pebble. A pebble becomes a rock. Over millions of years, these rocks, these planetesimals, grow. They drift through the disc-like stones in a slow-moving river. their gravitational fields gently sweeping up everything in their path. Some grow into boulders, then into mountain-sized objects, their gravity now strong enough to pull in neighbors with a determined tug. Collisions become more frequent, sometimes shattering, sometimes merging, in a grand, chaotic, but ultimately creative dance. This is how worlds are built, not in a day, but over eons of patient gathering. Every single atom that makes up our planet, the iron in your blood, the calcium in your bones, the silicon in the rocks beneath your feet, was forged in the heart of a star that died billions of years ago. The very water that fills our oceans and makes up most of our bodies is an ancient trave. It existed as ice crystals clinging to dust grains in that cold, dark cloud, journeying through unimaginable spans of time and space to arrive here. The carbon, the fundamental building block of life as we know it, is a gift from stellar furnaces that fused lighter elements into this wonderfully versatile atom. We are, in the most literal sense, made of stardust. We are walking, talking archives of cosmic history, and we can still touch this history. When a meteorite streaks across the sky and lands on Earth, it's not just a rock from space. It's a time capsule, a pristine fragment from that early solar system, preserved for 4.5 billion years. Holding one is like holding a piece of the cloud that birthed us, and we look out, too. With instruments like the Hubble and James Webb Space Telescopes, or the ALMA array in Chile, we are no longer just guessing. We are watching this process unfold elsewhere. We see the glowing disks of gas and dust around young stars, dark gaps within them hinting at the presence of newly forming planets. We are witnessing other solar systems in the act of being born. Even more profoundly, with observatories like LIGO, Virgo, and Cagra, we have learned to listen to the universe. We hear the gravitational waves, the ripples in space-time itself, from the cataclysmic mergers of black holes and neutron stars. These are the very events that forge the heaviest elements, the gold in a wedding ring, the iodine essential for life, and scatter them across the galaxy, seeding the next generation of stars and planets with the materials for complexity. It feels almost mythic, doesn't it? Like ancient stories of gods breathing life into figures sculpted from clay. The Earth, our home, is that clay, gathered from the dust of ancestors. The sun is our hearth, kindled from the embers of elder fires. It's a story that stretches from the unimaginably vast to the intimately small, from a collapsing nebula to the quiet miracle of a single conscious mind. And here we are, standing on a world of rock and water, breathing an atmosphere of nitrogen and oxygen, looking up into the night. The light from those distant stars, some of which are young, some ancient, some long dead, travels across the void and falls upon our eyes. That same starlight glimmers on the surface of our oceans. Oceans made of water that once drifted through the very space between those stars. Take a slow, deep breath. Feel that. That's the rhythm of now. It's easy to think of time as a straight line, an arrow shot from a definite beginning towards an inevitable end. But what if it's more? Like the tide, a constant ebb and flow, where every ending is just a prelude to a new beginning. We've spent this journey looking back, all the way to the edge of time, to the first light, and what we found wasn't an ending, but an overture. That faint, persistent hum, the cosmic microwave background, isn't a final echo. It's a lullaby, the universe singing to itself across billions of years, a gentle reminder of its own birth. It's the oldest light we will ever see, a baby picture of the cosmos, still glowing in the background of everything. When we look up at the night sky, we see galaxies not as static objects, but as ongoing sentences in a story that has no final page. Each spiral, each cluster, is a new clause, a fresh thought in the cosmic narrative. We are living inside an unfinished epic. For as long as we've been human, we have crafted stories to explain where we came from. The Mayans envisioned a world born from the thoughts of creator gods. The Norse spoke of a cosmos emerging from fire and ice. Science, in its own way, offers us a new kind of origin story. It's a tale of quantum tremors, of a universe inflating faster than light, of a fiery fog that slowly cooled into transparency. These stories don't cancel each other out, they harmonize. They all speak to a fundamental human need, to understand our place in the grand scheme of things, to know that we are part of something vast and ancient. And the most beautiful part of this scientific story, it's full of mystery. We talk about dark matter and dark energy, not because we have all the answers, but because we have the courage to name our own ignorance. Not knowing isn't a void to be feared. It's an invitation. It's the universe leaning in and whispering, "What do you think happens next?" Every question we ask, every telescope we build, is our response to that invitation. From the first quantum flicker to the slow, patient gathering of dust into stars and planets. From the dark matter scaffolds that built the cosmic web to the stardust that eventually learned to think, to feel, to wonder. That stardust is us. We are the universe's way of knowing itself. A brief, incandescent moment of awareness in a story that spans eons. There is a profound gratitude in that realization. A sense of being home, not just on this small blue planet, but in the cosmos itself. So, the next time you stand under a sky full of patient stars, or even when you hear the faint, random hiss of an untuned signal, remember, you are hearing the echo of creation. You are part of a story that is still being written. The journey to the beginning of time hasn't given us a final answer. Instead, it has given us a more beautiful question and a universe of possibilities to explore. Thank you for joining me on this voyage to the edge of time. It's been an honor to share this wonder with you. If this series sparked your curiosity, please consider liking this video and subscribing to the channel. I'd love to hear from you in the comments. What cosmic mysteries should we explore next? Until then, keep looking up, keep wondering.